All right. All right. Before I start, I guess because I saw a few more people walk in, last call to check in, just so we know who's attended. It's for our own statistics. It's not going to have any effect on you, so don't worry about that. Before we start, I wanted to just some few disclaimers. This is a relatively big classroom. I have a mic here, but I might be walking away from it to get to the board. So if at any point you have trouble hearing me or something, please feel free to raise your hand, let me know. Or if you don't understand something, there's a section dedicated in the end for about 30 minutes of questions and answers. But if you have questions during the workshop and you don't think they can wait, you can also raise your hand and ask. And before we start, there's a few logistical things. For DS3, if you haven't signed up already or if you haven't heard, next Wednesday, we are doing an office tour for Click Health. So Wednesday, 2 to 4, they're inviting us to their office. We're going to go over, have a tour, learn about their business and such. And yeah, that's next week. The sign-up link is there if you're interested. Or if you think someone else might be interested, you can take a picture of that, send it to them. Yep. Good? All right. I'll give you guys a few minutes, maybe like 1 minute. All right. So this was the pre-installation. If any of you still haven't figured this out, we have a few other DS3 members in the back. You can raise your hand and they'll come help you. So the plan for today, this workshop is going to be split into about 2 halves. The first half is dedicated more to theory. So I'll be going over some of the common data engineering topics and terminology you'll see, as well as some general good practices that you'll probably pick up. For those of you who don't know me, my name is Bob, or I go by Guo Cheng, and I'm a 5th-year mathematics and statistics student at UTSC. And for my co-ops, I've worked for about a year full-time as both a combined data scientist and data engineer. So I have worked with all the same Python pandas, data analysis projects, and then I've also worked with data engineering from the raw data sources all the way up to the Power BI reporting and reporting models and such. So yes, first half is theory, terminology, and then we'll have a short break. During that break, if you want to get more food, go ahead. If you want to ask questions, go ahead. And then after that, we're going to get into the kind of technical portion where I will introduce some concepts about SQL, and we'll use Python and SQL, explore some databases, and get a chance to build a very simple Python pipeline. So let's get started. I think the most important question I have to answer before, or for any data engineering workshop, is what is data engineering? And to be frank, data engineering is taking data and making more data out of it, or making tangible things from it. So for those of you who want to compare data engineering and data science, science is the idea of asking questions and answering questions. It's testing hypotheses. Whereas engineering, if you look at traditional engineering, electrical engineering, it's all about building things. And data engineering is no different. It's about taking data and building things with that data. So for us, engineering is more in terms of efficient storage. We use it for reporting, and it's also an important part of data science as well. A common thing you might have heard even before this workshop is the concept of the ETL process or pipeline. That stands for extract, transform, load. Hopefully, by the end of this, you'll have a very clear understanding of what all that is, but we'll cover that more a little bit later. So the main differences, I mentioned earlier, data science is a science. It's taking data and it's using it to answer questions. Science is all about taking what we know and asking questions, finding answers to those questions. Whereas data engineering takes data and creates more data. No matter what you're making with data engineering, you're always going to end up with some kind of extra data, whether that be a single summary or your cool graph. You're making more things with it. You're organizing, categorizing, or summarizing into other forms, and you use it often for visualization. So whenever after a midterm, your professor pulls up on the slides, oh, here are your midterm statistics, here's that grade distribution. You go on CrowdMark, you see how you did on CrowdMark to give you that bar graph. It's all data engineering. And more importantly for us, because I'm going to guess a lot of us have an interest, or at least some passing interest in statistics, Data engineering is used in almost every part of data science. So it might not be apparent while we're working on school projects because a lot of the data sets we're given are pre-engineered. When you're working in a professional field, almost the first 3 months or so of any data science project is actually dedicated purely to engineering, and that falls on the data scientists as well. So common data engineering tools, you'll see we'll be working with some of these, but these are ones that you'll likely see at least one of these in any data engineering or data science job you'll work at. Some of them will be pretty familiar, so you've probably seen in the bottom left corner there, that's the logo for Amazon Workspace. You might have worked with Tableau. I'd guess the greatest majority of you have worked with Python, the Python library pandas. SQL is huge in data engineering. And then you have some other modeling software like Tableau, Google BigQuery, and Power BI. So let's go over some of those common terms and conventions. First things first, data pipelines. So a data pipeline you can think of as, well, a physical pipeline also. It's something that moves data from one place to another. But I'd say the closer representation is something akin to a conveyor belt or maybe an assembly line. It's a combination of various operations and tools designed to change the structure of data and move it between systems for various reasons. So there are multiple kinds of pipelines, of course. Sometimes you might be working on a one-time project. So for example, at the end of the quarter, at the end of the year, your boss might say, hey, make a end of the quarter, end of the year report for us. And you need to pull all that data from your database somewhere. So rather than spending 3-4 days going through all your tables, copying and pasting into Excel sheets and using like Excel formulas and such, you could spend a few hours, build a data pipeline, click run it once, and everything is done. And you can delete the pipeline and never think about it again. Or for a lot of places, they might have daily or automated loading things. So they might have, for their customers or for their internal database, live updating reports just to see how things are going. There's no one in the background who is pressing a button every hour to load that data. Those are all automated pipelines, which are sometimes called jobs. So when we're working with data pipelines, there are 3 terms that you will hear very commonly, and those are wrangling, migration, and integration. First things first, integration and wrangling are the most commonly used. Integration is to take data from raw data sources, so maybe from another team's Excel sheet, maybe you sent out a survey and you're getting the results back from that survey, maybe you're using some sort of scientific equipment and that equipment's feeding you back CSV files, and you're putting it into your database. Wrangling is the general term for taking data, changing its form in some way, shape, or form, doing some joins in SQL, finding the mean, all that kind of stuff. And then migration is taking things from one database and moving it to another for whatever organizational purpose. So back to the concept of ETL pipelines. Integration, wrangling, and migration should sound very familiar to ETL. In fact, ETL stands for extract, transform, load. And it's not a sort of technology per se, it is more a methodology that has been developed over the years. So every data pipeline you will likely run into uses this common idea that it does some of these 3 things. It might not do all 3. You might have a pipeline just doing extracting and transforming. You might just be loading. You might be transforming and loading. You might just be extracting and loading without transformation. But it's some combination of these 3. And so it's helpful to understand what they mean. Extract is to pull data from some source. Transformation is exactly what I said for wrangling. It's changing the data, it's transforming it. And loading is saving that data somewhere else. Now, this is a diagram that you might see in a lot of, if you Google what data lakes data engineering is, you'll run into this diagram a lot. This one I pulled from, I think, Altexsoft. This is a very simple apply diagram, but hopefully we'll be able to understand what all of these are. We just went over the idea of a data pipeline. We talked about transformations, but now we're going to talk about the kinds of databases you'll see. So first things first, I want to talk about the data warehouse. A data warehouse is a relational database, and it's normally medium to large size. When I say medium to large, I mean you're dealing with anything from about, I'd say, 100 gigabytes up to maybe 100 petabytes. Or sorry, not 100 petabytes, about 1 petabyte. And a data warehouse is used to store semi-structured data. So it's data that's kind of in the middle of being transformed. You might see other names for data warehouses. Common synonyms I've heard are staging zone, staging area, the SZ. It's basically, if you're doing data engineering, it is the stage on which you are doing that engineering. So it's where all of your sort of scripts and codes are. And these data warehouses tend to have very clear internal relationships. So if you have a data point in some table, let's say you're looking at an employee and that employee represents a data type, you'll be able to search up that same employee in other tables in that warehouse, and you'll be able to clearly find everywhere they appear. They have this very clear sort of tracing and relation built into them. And more than that, data warehouses are also often categorized into things called schemas. Now, there's no technological advantage to schemas. It is more of a really good practice naming convention. When you run into tables in data warehouses, they will look, if I can find my eraser, they will look something like this. So you'll have a table name. You might have, I don't know, table 1. And before it, you will have .schema. This schema is like a categorization. So sometimes, if your table is a pure raw data source, it might say raw. Or for any of you who have heard of Salesforce, Salesforce has their own schema. If you import something from Salesforce, it's often called SF or SFDC. If you've worked with SAP, it might be SAP. If you have reporting in Power BI and these tables are engineered to be reported on, they might have Power BI. The idea is that the data warehouse is partitioned into this sort of schema where if you wanted to know what each table was being used for, you could just look at its schema rather than looking through and asking a bunch of people, looking through some very complicated blueprints. It's there for people to do. And not only is this nice for us, but it also makes SQL querying a lot easier. Imagine if you're working on a job and you think you have to do this really complicated engineering, but you're looking at a raw table, and then somewhere on a Power BI table, it's already there and engineered for you. Now, on to the concept of a data mart. A data mart is a way smaller relational database. I'd say it's closer to about 100 gigabytes. And it is intended purely for production. So you'll often get one data mart for each team in a company, and it's intended for completely engineered, not raw, like cleaned and prepared data for that team to use. And the idea is that this allows for data engineering to be more centralized. There is no requirement for at least one person on your team to be a data engineer. You could have no one on your team who's good with engineering and have a centralized team providing you, well-made structured data. And so everything in there is perfectly structured. It's intended for the business to do their own reporting, to do their own graphs. If you ever look in like a sales department or a human resources department and you look at like their spreadsheets and all that, those are likely coming from a data mart. Now, it is of course worth mentioning, in recent years, big data has become very popular. And some of you might have a very clear sense of what big data is. And in honesty, big data is an extension of what we have for existing data engineering. So it's worth noting that the concept of data warehouses and data marts, I mentioned they're all kind of based on the size of the database. And so if you have not that much data, if you have a very small company, maybe you've just made a startup, the idea of a warehouse, the idea of a mart, it kind of blurs together. You'll see a lot of companies who are just using like one database, and they say, oh yeah, this part's our warehouse and this part's our mart, and it's just the same database. It blurs together the smaller your data is. But when you get to bigger and bigger data, we actually need to introduce more things because data warehouses cannot handle the amount of data that is in big data. So big data literally means tons and tons of data. A good example is, I believe Google sent out a report a few years ago saying they handle about 10 to 15 exabytes of data. And if you have a hard time grasping what an exabyte is, the MacBook Air, or the MacBook Pro, pardon me, that I am teaching this workshop on holds 1 terabyte of data. So it is 1,024 gigabytes. A petabyte of data is 1,000 1,024 terabytes, so 1,024 of these MacBooks. And then an exabyte is 1,024 of those petabytes. So it's a huge amount of data. And the thing is, those data warehouses, they cannot handle it. Because once you're dealing with these tons and tons of data rushing into all your systems, you have a hard time controlling it. You can imagine, the more data you have, the more chance you have for errors, for corrupt data to be rolling through. And so they introduced the idea of a data lake. And a data lake is just a pile of raw data. There's almost no structure or engineering in the data, just a pile of stuff. And the idea is when you get a huge data dump and it's hundreds of petabytes, you just pour it into the data lake, and then people will scoop out the data they need later. And this sort of methodology works because now you don't have huge clogs of data in your warehouse. You have a big centralized pile for all your data. When you're working with something, you take it into your warehouse. When you're done, you're moving it into your data mart. Now let's talk about the data itself. It feels a bit strange to talk about such a low-level concept, but data in data engineering has a very specific term. So you've worked probably with a lot of different tables in your lifetime, but tables are very well defined in data engineering. And in data engineering, they look exactly like that. So when you're looking in a data warehouse or just any database, tables are separated or are categorized by their columns and by their records. Records are what we call rows. I'm not sure why it's the case. I think it's just because of what rows represent. But a column is what you're used to. It is a vertical categorization of a single data point. So a column is the representative of something that all of your data will have, whereas the record is the representative of a single observation or a single trial. So for example, suppose if you've ever worked with regression analysis in statistics or any kind of linear modeling or general modeling, you know that you have these variables and these trials, and they store different things, right? Your explanatory variables can be your columns. So if you're looking at treatments, they might be the dosage, the age, the demographic, the symptoms, and then each record is a single observation. So each record is maybe an individual patient for which they have exactly one age, one treatment type, one demographic, things like that. So in statistics, we call these explanatory variables for columns, and records are observations. This is just so you can make that connection, but in a table, in any database, they'll look like this, where records are rows and columns are columns. And within these tables, you will see two very important types of columns, and they're known as keys. So keys, very simply, are columns that hold some kind of identity. Now, notice I use the word columns here and not a column, because sometimes a key might not just be one individual column. It might be created from a combination of two columns. So a great example is if you're working with perhaps a group of people, maybe you're working in human resources, and you don't, for whatever reason, have an employee ID, and you only have their names, you might run into like 5 or 6 people whose names are Sam or Bob, but you might only run into one Sam Smith, one Joe Smith. So the combination of these two columns forms a stronger key. In computer science, you have a similar concept. It's not a perfect comparison, but it's kind of akin to a public or a global variable. The idea is that this key should be the same throughout your entire database, and anything that's working in that context, that project, should have the same key. And there are two kinds of keys. Firstly, a primary key is the unique identifying column for each record. So we sometimes call it an index. And for any given table, each record has its own unique primary key. So in a table, if you know what your primary key is, no two records will have the same primary key. And this is useful for many reasons. For one, it lets you tell apart data from another. You don't want two data points to be almost the same and you get them confused. And for another, from a computing standpoint rather, it actually optimizes SQL queries a ton. I have worked with tables where I'm trying to write like this medium complexity query, and it says it's going to take 20 minutes to run and give me some data. And I could just, I could click run and I could go to lunch. Or I could check a box and say, oh, this column is my primary key. And suddenly that 20 minutes becomes 10 seconds. It's a huge difference because it allows the computer to easily categorize what it has scrolled through and what it hasn't. Aside from a primary key, you also have a foreign key. Foreign keys are a little bit harder to wrap your head around. They look they look similar to a primary key, but they are a primary key for a different table. And this is where the concept of relational database comes in. All these relational databases are related to each other by name, of course, in some way, shape, or form. And the way those connections are made are through primary and foreign keys. So an example in the next slide that comes is this. So you might notice, first things first, foreign keys are not unique because they are not your primary key. They don't have that requirement. But we have table 1, table 2. Table 1 I have indexed with letters, so A to K, and then table 2 I've indexed with numbers. And you can see that if I wanted to build a relationship, a strong relationship rather, between table 1 and table 2, I need to have the keys for table 2 stored somewhere as a foreign key in table 1. That's where the idea of being foreign comes from. It's a key, but not for the table you're currently looking at. And these are the essence of relational databases. They allow for you to join and trace data very easily. So let's say I wanted to see where whatever record in table 1 appears. I say, OK, I'm interested in the record labeled A. Well, I know that record labeled A is labeled 1 in a different table. And if I have a third key, it might be labeled A1 in another table. This is how you would trace data. And you're often asked to do this, especially when you're looking for what something went wrong. You say, oh, this person, I have to track this person down in my database and change a little bit of information for them. Now, these relationships, they give rise to 3 kinds of connections. And these are one-to-one, one-to-many, and many-to-many. So a one-to-one relationship is, if you can think of in math, it's a one-to-one bijection. For each element in one table, there is exactly one element in the other table that it maps to, and that encompasses just about every element in both tables. A one-to-many is like a surjective function. For one key in one table, it might map to two or three records in another table, or vice versa, a many-to-one. You might have many foreign keys in one table that map to one key in your table too. So we can look here. The connection between A from 1, this is a one-to-one, whereas you can see that 4 repeats, but it only maps to 1. So this relationship here, caused by this foreign and primary key, is a many-to-one because you have the idea of repetition going into one record. And then you have the biggest kind of relation, which is the many-to-many. Now, it might be hard to visualize just from these definitions, but when you're doing your data engineering, when you're making these relational databases, a many-to-many relationship is often quite bad. You'll have almost every software you see, like Power BI or something, they'll have an option to make a many-to-many relationship. But when you make them, you know it's bad because your program will probably freeze or crash. Honestly, it's because if you think about it, if I have 2 tables here, right, 2 very poorly drawn crooked tables, a one-to-one relationship, let's say I have 5 columns here and 3 columns here. A one-to-one relationship, it doesn't make any difference. At most, I might have, I can't write that. At most, I might have, 5. At most, I might have 5 columns total in this relationship. Whereas if I had a many-to-one relationship, suddenly it's whatever the biggest of the 2 is. Suddenly it is whatever the biggest is. So it's multiplying them together, right? This might be connected to 2. So now I have 2 relationships. This is an extra relation, or this is an extra column. This is an extra 2 columns. So you see the number of relationships you have in your database will result in the number of columns you end up with being stored by the computer. If you have a many-to-many, you can see it's going to be a huge mess of connections. Like you'll have connections going any and everywhere. And this is just, it's a huge mess for your computer. It's a huge mess for whatever database you're looking in. If you define a many-to-many relationship, you'll notice a lot of your data models suddenly start bloating and they have a bunch of extra copies of like hundreds and hundreds of columns. And when you're working with tables that have millions of columns, you don't really want to deal with 1 million squared. And so it is common practice, it is good practice, to avoid as many foreign-to-foreign key, many-to-many relationships as possible. There are a few ways to get around them. One of the ways we get around them is with a concept called a mapping table. Now, a mapping table is unique in that while it is good practice to have primary keys for most of your tables, mapping tables don't necessarily need to have primary or foreign keys. A mapping table basically stores only keys, but it's a way to let you take a primary key in one table and categorize it into a mapping table in another. So a great example of a use for a mapping table is for any data source where you're not sure how many columns you have. And it's a deceptively simple concept. If I asked one of you during a hackathon, say, hey, make me a relational database that stores recipes, and I want you to store the ingredients, and I want you to store, the steps in each recipe, you think, okay, I have a column for each ingredient, I have a column for each step, and the more you work at it, you think, oh no, this recipe has 3 ingredients and 5 steps, this recipe has 10 ingredients and 12 steps, I don't know how many columns I should make, should I just have 100 columns and then leave them blank if there's nothing there? That's very inefficient. Instead, you would use a mapping table. So you might have something like, this is your recipe table. So this is recipe. Ooh. And rather than storing ingredients, you have the key for your recipe. Maybe 1, 2, 3, 4. And then you have your mapping table. And this mapping table's pure responsibility is to map your recipe to its ingredients. So maybe you have a mapping from recipe to ingredients. And it's looking at it, and it's like, OK, these are my recipe keys. 1, 1, maybe 2, 2. They don't have to be unique. And then these are ingredient keys. Maybe these are A, B, C, D. And then these ingredient keys might map to a third table that has, ingredients. And then, this is stuff about the ingredient. So now you can see, rather than having dynamic columns, now I say, oh, this one, it's mapping to all of these recipes. This one is mapping to all of these ingredients. And then from here, maybe this is A, B, C, D. These are now mapping to their ingredients. And now I have ingredients as a vertical storage rather than storing them horizontally as columns. And I can store recipes vertically as well. And there's no longer any issue with having to add 100,000 columns to account for your recipe. So this is the main use of a mapping table. But you can also clearly see that because mapping tables don't need primary keys and can store only foreign keys, there's also a way to turn any many-to-many relationship into two one-to-many relationships by shoving a mapping table right in between them. Now, I've talked a lot about keys. And alongside keys, you need the concept of data granularity. Now, data granularity is a topic that I actually grappled with for many months when I first started working, because every time I was still learning, I didn't know what I was doing. Every time I had a question for my team, I wasn't sure how to do a join or how to do a SQL script, I would ask them, and the first thing they would always tell me, without a doubt, was, what are the granularities of the tables you're working with? And me, I was too stubborn to Google what it means, and so I waited for someone to tell me. And here is what it actually means. The granularity of your data is the direct measure of how much detail is in your record. So the maximum amount of detail you can store in your data. The granularity of a table is that highest level of detail to be achieved by the table. These two words are synonymous. So if you think of a data set with a higher level of detail, it also has a higher level of granularity. So a great way, let's not talk about that yet. A great way to think about granularity is time. Time is a classic example. Suppose you were running 2 experiments, right? And you were recording the data for each trial in your experiment. Experiment 1 is measured in terms of seconds. Experiment 2 is measured in terms in terms of hours. So what do I mean measured in terms of? I mean every second you get a new record for experiment 1. Every hour you get a new record for experiment 2. Now, who can tell me which one of these has a higher level of granularity? If you have an answer, you can raise your hand. If not, I'll answer. Yes?
Seconds?
Exactly. The seconds has more granularity because think about how many seconds are in an hour. I should have chosen an example where I would easily know the answer. But for every one record you get in experiment 2, you're getting, 360 records for experiment 1. So you're getting way more detail. Even if the change is minute, that level of detail, the resolution of your data is way higher. And you might think, wow, data granularity is great. I'm going to store everything in terms of milliseconds and nanoseconds, get as much data as I can. But you do have to balance it. Because you can think, I mentioned earlier, the data set you have for experiment 2 is going to be 360 times smaller than your data set for experiment 1. So if you only have so much space, you don't want to bloat all of your storage devices with unnecessary data. But one place where data granularity is great is for picking your primary key, because I mentioned primary keys are unique. They are the unique identifying thing for each record. And so they also end up being very good indicators for what your key or for what your granularity is, and vice versa. If you're trying to pick your primary key, the granularity of your data is a very good pick for what that key might be. So maybe you want to categorize each record in all of these experiments. You could write a script to say every time a new observation comes in, I'm going to label this one 1. And then new record comes in, I check, I've already said 1, I'll label this one 2, 3, 4. You could label it 1, 2, 3, 4. Or you could say, hey, this one came in at 12 a.m. on March 31st, 2024. This one came in 1 p.m. March 31st, 2024. And that's a great primary key. Or if you have employees, I often see that employees are categorized both by their employee ID and the month and year they were employed in. So if if 1 month they get promoted, you get to see that in the previous month, even though it's the same employee, at one point maybe they were an analyst and then they become an associate, maybe they're an associate, become a manager. It's a great way to differentiate between things where you might not have necessarily at first seen differences. And then, of course, the question I posed earlier, higher granularity always better, why or why not? Ideally, you would like higher granularity, but you also have to make sure to balance, not overloading all of your data and not having unnecessary data. Like, for example, back to that employee thing, there's no need to store who your employee is every second of the day, maybe once a day at max, maybe once a month. Yes?
Wait, could you please clarify the third sentence? When choosing your primary keys, the granularity should have a one-to-one correspondence. What does a one-to-one correspondence mean?
One-to-one correspondence, that's a good question, means that for every one primary key you choose, there should be one of the highest granularity thing in your table. So if your granularity is, I mentioned hours, for every unique primary key you have, it should roughly correspond to one unique hour in your record. So a better example of this might be something on the employee level versus on the team level. So you can think like a team has maybe 5 or 6 employees. So for each team, you might have on the team level, team granularity, you only have 1 column, whereas on an employee granularity, you would have 5 or 6 columns. The one-to-one correspondence means that for each primary key you have in your employee table, it corresponds to 1 employee in that table, because it is the employees are the highest level of granularity, whereas on your teams table, the highest granularity you have is by team. And so for every primary key you have, it corresponds to 1 team, maybe. Does that make sense? Yeah. Okay. Now then, this is kind of everything that you need to know for data engineering. There's a lot of extraneous stuff that you will run into, but I'd say it differs a lot between the company you run into. That kind of falls into the kind of company you're working for. So if you're working for sales, you might be working with more monetary related. You might have you might be dealing with lots of regions, lots of money. If you're working for IT, you might be dealing with more products. You might be dealing with more runtimes and like storing error codes and all that. So though I want to keep this as general as possible because I was hoping for a very large demographic of people to attend. And this is the stuff you will see in almost every data engineering job. The rest of it, I believe, you can map it very closely to what you've learned here, but it's more program specific. Now, there is one thing I want to get into. I'm going to describe it once, and it's something that you might run into when you're approaching senior data engineering, or when you're approaching maybe your third or fourth year as a junior data engineer. That's the concept of higher dimensional storage. So these are called OLAP cubes. They don't have to be called cubes. They could be rectangular prisms. They don't have to be 3 dimensions. They could be 4, 5, 6. It really depends on the situation. But these cubes are very detailed clusters of data that are produced and stored only in data marts because they are so heavily engineered. There's no point in storing them as raw data. They are almost always given to businesses so that they can easily do reporting and such. This is a 3-dimensional OLAP cube. It's way easier to describe. This one specifically, it's talking about the products they sell in certain regions and through certain quarters, which is a measure of time. And you might think, oh, what is the point of storing data in a cube like this? Well, in a cube, you can do very simple operations on all of the data. So let's say you have this big, complicated OLAP cube, and you have no idea what you want. But you want a table that has all of the amount of products you have sold for each reason. You don't care about the time. You have this cube, and you say, OK, I'm going to sum over one of the axes. I'm going to sum over the time axis, and then suddenly you are left with this 2-dimensional regular table. Or maybe you say, I don't care about the quarter, but I'm not worrying about the sum. I'm worrying about the average. You could take the average over the quarters. Maybe you look at how much you're selling during the quarter, but you don't care about your region. You could add up all of your regions. You could take the average over all of your regions. Or maybe you don't like how the regions are in your columns and how the products are in your rows. You could pivot your cube. You could turn it, and then suddenly your products are your columns and your regions are your rows. And so, or if you're only interested about maybe quarter 1 sales, you could take a slice of this cube and look at it from quarter 1. It is the idea that these weird geometric things you could do to a cube, if your cube is storing data, it also properly manipulates your data and gives you easy access to a ton of different tables stored as a singular object. And within each of the cells, and there's in that orange cube, which is indicated by a cell, it's normally either one data point. So you might see maybe a revenue, so a number representing revenue. You might see a number representing units sold. Or if you want to be more complicated and more fancy, it might store the key to another table. This is something called a drill down, where if you want more data or more detail in your data, rather than having a big cube, you have small cubes that all point to each other. And so you say, I want more detail for TVs sold in the USA in quarter 1. It's a little key, or it's a key, it points to another table, and then you have a table or maybe another cube that's dedicated purely to that kind of data. Now, this looks complicated, but for those of you who are in statistics or have worked commonly with statistics and categorical analysis, well, actually those of you who are taking C51 or have taken it, you have actually run into OLAP cubes before, and you might not have known it. And in statistics, they are called contingency tables. So you might have heard of a 2x2 contingency table. And I learned these personally from STAC 51. But you might have seen these in other classes. I would say it's very unlikely you don't run into these at some point. But it's the idea of maybe you're looking at treatments. So you say I have, treatment 1, treatment 2, and you're measuring if the patient improved or not. So maybe here it says they showed improvement, and here they said there's no improvement. And you have a 2x2 table, and it's counting. Maybe I gave 100 people each treatment, and for treatment 1, I saw 90 people improve, 10 people didn't improve. For treatment 2, I saw 95 people improve, 5 people didn't improve. And these are 2x2 contingency tables. And then as soon as you learn these, they'll introduce what's called a stratified contingency table, where you say, maybe this is for hospital 1, right? Hospital 1. And maybe I want to do the same thing for hospital 2. So now you have the same table for hospital 2. Maybe you want more hospitals. Hospital 3 now appears. Hospital 4, hospital 5. I could keep going, but if you look at it, it's just a bunch of the same 2x2 tables storing the same kind of value. We already have, two axes. This axis is for treatment, this axis is for improvement, and suddenly this axis may be for the hospitals. And this is an OLAP cube. This is designed as an OLAP cube. And so the reason these exist is because a lot of experiments themselves, the nature of their experiment, lends very well to this kind of data structure. And so it is helpful. You might not need to know how to build these, but it is helpful for any job where you're working with data, you're working with reporting, to understand what these work like and the things that you can do with them. And for anyone who has taken courses like these, you'll know that there are very well-defined and very complicated functions and formulas to calculate things directly from this table. I'll leave this up for now, but this is a lot to kind of take in, but luckily, this is the end of the theory portion. So everything that I have said up till now are sort of general convention and theory you will find in just about any data engineering job. For now, we'll take a small break. If you want to get some water, go use the bathroom, ask some questions, or if you want more food, there's food here. We'll take a break for maybe 5-10 minutes, and then we will come back and we will start the practical portion with SQL and such. Yes. Now proceed to the, where am I? So we last left off here. This is the small break. We will now proceed to the more practical part of this workshop. Now, in the workshop description, I mentioned that we'll be building our own data pipeline. A little bit more information on that. We will be trying to imitate and make our own small version of Acorn. So whenever you go on Acorn and maybe you click, academic history or something like that, you see all the classes you've ever taken, and you see your score, the class score, and like the averages, right? And then that appears in all your transcripts and stuff. We'll be making a version of that. So first things first, there are a few things you'll need for here. We mentioned it earlier. You will need to download files from this GitHub. So the GitHub repo, if you follow that link, where is my mouse? If you follow that link, it looks something like this. You don't need to set up any environment in this GitHub. There's no complicated Git stuff you have to do. Literally, you go to code, you go to download zip, and you just download every file in this GitHub repo. And once you do, you just save it. You save it into a folder. For me, I have it saved here. It's not showing up. That's great. For me, I just have it saved on my desktop. You could put it anywhere you want. But it's just a folder. You should have these files. You should have something called acorndb. This is a project file. You don't have to worry about this. And then you should have 6 CSV files. And we're going to be exploring these throughout the next half of the workshop. Now then. So first things first, I think it's kind of obligatory that I talk about what SQL is. So SQL, if you don't know, stands for Structured Query Language, and it is the most popular language used for database management and sort of data management, especially for relational databases, which I spent the last hour and a half talking about. And it has become like almost synonymous with the industry standard. It, I believe, turns 50 this year, which is, quite well timed. But it has become so popular that rather than making your own language, a lot of companies are just taking SQL and adding their own little things to it and packaging it as the new SQL. And so you end up, after all this time, with a bunch of what are called SQL dialects, which they have all the same properties of SQL, but they have maybe a few extra functionality here and there. So you might see popular ones like PostgreSQL, TransactSQL, MySQL, SQLite. These are all versions of SQL. SQL functions that work in one, then your base SQL will work in all of these dialects, but they might have additional functionality, might work a little bit differently behind the scenes. The one we're working with is called SQLite. And as the name suggests, Lite is a very lightweight version of SQL. When you first look into SQL, you'll see that when they ask you to make a database, it's always, oh, find some sort of machine so you can host your server, buy an Amazon Workspace package, host it on there, right? It's all like server-based, whereas SQLite is way simpler and it's way better suited for teaching. It's all file-based. So everything in SQL can be stored in a database file. It's a very small database file. The entire workshop fits in like 33 kilobytes. It's great. And you see these really often in just apps. A lot of apps have to store some kind of client-side information, some memory. And those often always come in the form of a SQLite server. It's just a database file that gets stored. And it's read and written to almost like a CSV, like any sort of Excel or CSV file. And it's very fast. It's originally, I believe, written in C, so it is very well optimized. And it's very well used behind the scenes. Now, it might not be a surprise to anyone that I can't teach a full language in the, hour and 28 minutes we have remaining. And so I'm going to provide you with this link. This is you've probably heard of W3 Schools. W3 Schools, the idea is that I'm going to go through some important SQL keywords like, select, join, union, all that kind of stuff. But I want you to be able to look at how all of these keywords work anyway. This is the page for base SQL. So anything that you see here should work for anything you see in SQLite bar, SQL databases. But yeah, I want you to be able to refer to this while we're working through the next half of the workshop. It's a supplement that I think will be helpful rather than having me go through and explain what each keyword does. Now, I mentioned earlier, SQLite is a very lightweight functionality. It cuts out a lot of things, a lot of the glamour that's in normal SQL. And something that I find quite funny is SQL is one of the few languages, in SQLite rather, that doesn't store data types. So you might, if you've worked with SQL before, and when we get into SQLite through DB browser later, you'll think, hey, a lot of my favorite data types, where's date time, all that stuff, why is it all gone? Well, SQLite doesn't really care about your data type. It just says, okay, if you're in this general group, we'll call you an integer. If you're in this group, we'll say you're text. If we don't know what you are, we'll call you a blob. If we have a general idea, you might be a real. If you're some kind of number, maybe you're a date, maybe we don't know, you're a numeric. And it's all these 5 types. You might think, oh, your favorite data type is missing. It's not. It's just been collapsed into one of these. Now, let's move on to DB browser for SQLite for a moment. I want you guys to, if you have it downloaded, open up DB browser. And DB browser, when you first open it, if my doc would show, but it does not. There you go. It should look something like this. Right? It's mostly blank. It's got nothing in there. And we are going to use this. Is everyone, actually before I do that, is anyone not able to open DB browser right now? And like they're able to, oh, yes, you need some help? Yep. It's probably in your downloads.
Yeah, I mean, so I finished the setup wizard.
Yep. Yep, you've got it.
And then let's see, I want to change something, and then I don't change it, really.
Okay.
Let's change.
Okay, and then you can't find it.
Yeah, nothing really happens.
Interesting. Where's Adi? I think Adi will be able to help you with this more than me, because I don't use Windows very often. Yeah. Adi, he can't find his DB browser. He's installed it with the wizard, but he doesn't know where it's appeared. All right. All right. So in DB browser, I want you guys to open up the database that's in your file, so that I've sent to you, basically. So here, I want you to click on Open Database, and then just navigate to wherever you have saved the GitHub files I had you download earlier. Select acorn.db, and click Open. Yep. Oh yeah, you can take some time to look for it. You go to open, oops. And then you just navigate to wherever you put your file and you click on acorn.db. Right. If you've got it open, you can give me a thumbs up. Or if not, thumbs down. Yeah. Right. Oh. It's, oh, DB, the link for DB browser isn't there. Hang on. Oh, you got it? Okay. All right, I'll go slow. Let's take a look at what we're looking at. So within DB browser, we just opened up the Acorn database. In this database, you'll see 4 tables. 2 of them you'll notice are labeled as raw, and 2 of them are labeled as view. And even the database categorizes them differently. The raw ones are called tables. The views are, rather conveniently called views. The difference between them I will get into very shortly. But if you want to explore each of these databases, you can click on the Browse Data tab and just select one of these 4 tables in the drop-down, and you can see that it's a table. It holds things. I mentioned earlier, these are your examples of records. These are your examples of columns. It's a table by definition. And then you have view, you have the raw for B57, have the view for B57. What I've given you is essentially 2 simulated classes. I generated the grades for these. I generated the student numbers. These aren't real grades. I'm not going to call someone out for failing B52. Right? These are just generated grades that we're going to get to work with for the remainder of the lecture. And before we move on to the pipeline, I want you guys to be able to navigate this thing. So first things first, we're going to add some data. I want you guys to go to, in your DB browser, go to File and Import. Oops. And you should see an option that says Table from CSV. You can navigate back to that GitHub thing that I had you open before. If you opened your project, it should reopen to this table immediately, or this folder immediately. But you might notice we only have 2 classes in here, but we have 3 classes here. We also have C62. So we're going to write the view, we're going to import C62, and we're going to add it in, or we're going to build the view here during this. So firstly, you can select C62 underscore raw, not new C62. Get the raw one. Click Open. You don't have to worry about all of these. This is just making sure it's all correct. You can check here that this is what the tables are. Click OK. And then bam. You notice a new table has been created. It's called C62 raw. If you click on the drop-down menu, you see all the columns. If you go to Browse Data, you can select it in C62 raw, and you will see the data appear. Now, the similarities, oh, is it too small? Oops. I can't make the data too much bigger. Yep. Can someone, OK, give me a minute. Yep. For what?
Where did I get the new data?
So it's in the, if you hit table from CSV, it's in the same, yeah, it's in that workshop file. And then it's CSV raw. There you go. Yep, and you can click OK. There you go. All right, so this is what each of these looks like. This is a little bit small, I will not lie. I cannot find a way to make it bigger. Oh, if you go to the Browse Data tab here at the top. There you go. Is that going to let me do it? No? Okay. Okay. So let's take a look at what is in each of these. So within the new table we just added, we have a column. This is a little bit small to look at. I'm going to guess you might have to look from your computer. The first column is for student numbers. These are just randomly generated student numbers. And I'm going to claim that C62, rather than a midterm, it has no assignments, no quizzes. It just has 2 term tests and a final exam. And like most courses, you can declare credit, no credit. So if a student has declared credit, no credit, this is just a string. It will say false if they haven't. And if they have declared it somewhere down here, you can see that there's the occasional student that is declared true. Now, if we look at maybe B57, you will see rather than the 2 term tests, they have the same student number. This is our key that's consistent between all 3. They have 3 assignments and their respective grades, a midterm, a final, and that same credit, no credit flag. But what do we add with the view? The view, we have all of the columns as before, but in addition, we now have the student average and the class average. And you can see for cases where they selected CR and CR as true, rather than showing the grade, it's instead just giving you the CR and CR. So in Acorn, if you don't know, if you declare credit, no credit, and they'll hide your grade. They won't tell you what grade you got. You just get the credit if you pass. If you didn't pass, you don't get the credit. Now, I want to, before I continue with this, I want to see what's on my next slide. Oops. I want to talk about what views are. And before I do that, I think it's helpful that I help you explore this database. So we've gone over these 2 tabs. We've gone over database structure and browse data. I want you guys to now move over to execute SQL, and you will come to what is basically an empty text editor. And this is where you can, within this tool, run SQL. So the first and most obvious, I want you guys to be able to query some data. So we are going to select. I really wish I could make this bigger. I don't know if I can. View, window layout. Do you know how to make this bigger? Yep. Preferences. Let's do like 25. Let's do like 17 or something. And then SQL results font size, editor font size. Let's do 20 for both. You guys don't have to do this. I'm just doing this so the presentation's clearer for all of you. There we go. That is probably a little bit clearer. Is that better for everyone? All right, thank you so much. So let's select some data. So when we hit select, select is a keyword that will only return a table. That is what select means. When you click select, you're saying, I'm going to select the data, and SQL goes, OK, here's the data. I only know what tables are, so I'm only going to give it to you in the form of a table. So looking at maybe B52 view, let's say that I want, ooh, that's a bit weird looking. Let's go to B57 view. Let's say I want the student number, and I want their midterm and their final grades. All right, let's say I want their midterm and their final grades. Oops. All right, so maybe I only want the student number and I want what they got for their exams. I'm going to say I want the midterm column and comma, I want the final column. And what table do I want to select these columns from? I'm going to say I want to select them from STAB 57 view. Oops. And let's just keep it simple. Let's just run this. There is a little play button above. Once you've written it out, if you run it, you see, bam, these are the midterm grades and the final grades. I forgot something very important. I want to know what students these are linked with, so student number. I run it again. There you go. This is the student number, the midterm, and the final grade. Yep. All right. Now, you can do a little bit more with this than just look at data. Maybe you can do conditions. So maybe I want to look at the grades for people who passed the midterm. So I can add conditions with the where clause, and I can say where midterm is greater than or equal to 50. If I run this, you see that here I have, 50 columns, right? This should say 50. And then if I run this, now there's only 40-ish columns, I think 41 columns. So all of these now, these are all people who have passed the midterm. If I want people who have passed the midterm and passed the final, I could add that in as an extra condition. I could run that, and now there's even less people, but these are people who've passed both the midterm and the final. More than that, I can curate columns. And a curated column, by the way, SQL doesn't care if you put in new line characters. You could put them anywhere. You could put a comma here if you wanted. It doesn't care where you put new lines. It's nice to categorize your columns like this. If I want to make a curated column, I could say maybe I want another version where it is, for some reason I want to double the midterm grade, or maybe I want to curve one. I want to say I want midterm, maybe I give everyone 5 points, plus 5. And I'm going to save this as curved midterm. Right? If I run this, now there is a new column here. And you can see this guy got 72.21 on the midterm. He got curved up to 77.25. This is how you would curate a column. And so in doing this, you can kind of make your own table however you want. You can give the instructions for how that table looks. You can do the same kind of instructions. You could do multiply, addition, subtraction. If you look in SQL, you can even do like max, min, and average as aggregates. But the idea is that we have this. And now, what is a view? Well, we have these cool SQL outputs, but we have nothing to really do with them, right? We can look at them. They're nice to look at, maybe. But a view is SQL's in-house data transformation process. Because you might think, hey, what we did there when we curved that midterm grade, that's technically data engineering. That's taking data and making new and different data with it. And that's what you can do that in SQL. You could do that in your pipeline, but you can also do very simple versions in SQL. And a view is a way of saving it. Intuitively, a view is a live updating select query in the form of a table. So when you run a select query and you want to have this query always available to you, you can save it as a view, and then that way, anytime the table that you were selecting from gets changed, maybe a student grade gets changed, that view, because it is a reflection, it's a literal window into that select query, that view will also change. And that's what views are. Views are tables that are made from other tables. They save some sort of select query, and that query becomes how the program builds that table. So if I go into DB browser, if I want to save this as a view, maybe I want to say this is called, I want to save this as my curved midterm, or my curved B57. I can say create view, call it curved B57. And then what do I want to save it as? I save it to be as this select query. So what this is doing is it's saying I'm going to create this view, and what am I going to create it as? As the result of this select query. So maybe I don't want this where clause. Maybe I want it to be just all of the students in B57, except I've curved their midterm grade up 5 points. If I create this curved B57, it will say on the side, query executed successfully. If I go back to my database, you'll see I now have a new view called curved B57. I go to browse data, I can select it, and you can see this is exactly what we were looking at earlier. It is the result of that SQL table. Now, if I changed anything in B57 view, it would also change in our new view here. So, knowing that, let's build the view for C62. Now, I mentioned earlier, I compared what the views did. The view adds 2 new columns. It's going to calculate the unweighted student average and display it for the student who has not declared CR/NCR. right? I say unweighted because I don't want to deal with grading schemes. I don't want to deal with someone who says, oh, our assignment was 40% of our grade. I'm just going to take the unweighted average. It's easier for all of us, right? And then also, I want it to have another column that says the class average. And that class average is calculated regardless of whether a student declared CR and NCR, because they get mixed in with all the other students. The hint here is that you can use an aggregate function. I am going to use the base sort of just like the function to calculate mean, but you can also use average, and this average becomes very important because these are all column-wise functions, and you can use them to calculate the average for all of a table. So let's build this view for C62. Now, a good practice when building a view, you can click this button up here. It looks like a kind of bit of paper with a green plus sign. It says Open Tab. You can also do Control-T or Command-T. It'll open up a new thing for you. Before you build any view, it is good practice to see what it's going to look like by building that select query first. So let us select something from C62, from the STAC62 raw that we imported earlier. Now, a bit of convention, if your table has like 100 columns, you don't want to write out all of those columns. The asterisk sign, that star, that will select every column in the table for you. So it's very nice, convenient. If you write the asterisk, it gives you everything. But aside from all of the columns, we want to make our own curated column. And the first column we want to make is the student average. Now, I mentioned earlier, SQL has built-in functions for mean and called average. They have max, min. But those are all column-wise. You see here, we're taking the average of the rows. So those functions don't work. We have to do it manually. So it's very easy. We just say, I want term test1 plus term test2 plus their final divided by 3. This is how you would calculate the average. And I'm going to save this as the student average. Now, if I run this function, you'll see there is now a new table here, or a new column in our result. That is the student average, and you can check the math. It is the average for each of these columns. But hey, something's wrong. This student declared credit, no credit, but we're still showing their grade, and we really shouldn't be. They got like a 14 or something. So we need to check for when that CR NCR flag appears. And we do that with SQL's version of an if statement, which is called the case when. All right? It's like if else, but it's case when. So let's say I want the case when CR NCR is equal to false. Right? If it's equal to false, then I'm going to do this. I'm going to show that average, and then I have to end my if statements, my case whens, with an end keyword. And if I run this, it's going to do that only then. Otherwise, it's going to print a null value. But if I don't want to print a null value, instead of end, I can add in else CR NCR. And then bam. If I run this, now whenever someone declares CR NCR, excuse me, that should be a slash, CR slash NCR. Now whenever someone declares CR NCR, it'll now say CR slash NCR. Now you might think, hey, at the end, if they passed, they should have CR, and if they didn't pass, they should have NCR. Well, just like in Java, or just like in Java, Python, any language you've worked in really, else you can do a nested case when. So I could say, rather than print this string, I do another case when, that is case when, oops, this sort of student average is greater than equal to 50, so this means they passed. Then I will say they get the credit, else they didn't pass, they get no credit. And then I have to do, I believe, another end, and then the end. So this is a bit confusing. I've written two end keywords here. This end keyword is for that nested case when, and then this end keyword is for the overall case. So it's the same as maybe your curly brackets. If you've ever worked in Java or C, you have to start and end it somehow. And in SQL, you end these operations with the end keyword. So that's why there's two ends here. But if I run this, and hopefully nothing breaks, perfect. Now we saw earlier this student got like an 11. He did NCR. And then if we scroll down, we might find someone, another NCR, another NCR. If they did pass, they would get a credit there. Now, we have the student average. Now, let's calculate the class average. And you might think, oh, perfect, put a comma here, by the way. If you don't have a comma, it's not going to like you. Put a comma here when you have to declare next column. Now you might say, hey, let's do the class average. Well, we can finally do our column operator, so we can just do average of, that big function we did earlier, and we can say that is as class average. And we write this and we think everything is going to be okay. For those of you who missed it, I can't stress this enough, put a comma at the end of your student average thing, otherwise it's going to break. You try this and you think, great, all right, our work is done. I run this and oh no, I only get one column. Did all 50 of my students drop? No. Create or average, and all of those max min functions are called aggregate functions. So I mentioned it in the hint here. They are aggregate functions, which means that they take all of the elements in your column and they will return you one result. But because it's one result, it is in the form of one record. So if you ever have an aggregate function in your SQL query and you don't give it any conditions, you're going to get one record in your output. To avoid this, there are many ways. Now, there are a few ways I could actually get by this. I mentioned in the first half of the workshop the mapping table. You could easily have some kind of mapping table that has, each class, maybe C62, C67, and then next to it, it stores the average for that class, and then you just use the SQL join to join that table on. But for us, there is a simpler way, and that is to use over. Over is a keyword that basically, it is harder to describe, but it says, if I give a condition in the over function, every time that condition is met, I'm going to print one copy of it for that group of records. So it's called a partition. You separate your records into these groups, and then you would run that aggregate function over each of those groups. But because I've not given it a condition, if you just put over empty, and you do that, suddenly it'll just say, all right, I'll calculate the class average for every single record. And so now we've fixed that problem. We've got all our students back. And now that class average propagates down all the way. And so if we look at this, this is exactly what we're looking for in that C67 view. You can take a little bit of time, snap a picture of it. This is the select query that is in your C67 view. I'll give you guys maybe 1 minute to snap that picture. And while I do that, I remember we've now verified this is great. So we're going to save it as a view. Or not C65, sorry, C62. So let's create a view and name it STAC62 view. Oops. Let me just check something real quick. Yep, that's perfect. And we're going to save that view as exactly this long-ass query that we have just created. Now, if I run this, hopefully nothing goes wrong. Perfect. In our database, we now have C62 view. We can verify, go into our browse data, C62 view, and bam, this is what we were looking for perfectly. So now that we've got this view, let's build Acorn. Oops. Before that, let's do joins. I mentioned joins earlier. I mentioned the idea of a mapping table, or how you could also did what I did with over. You could have a mapping table that stores each class and stores the class average for that class. And to do that, you would need to understand what a join is. So a join is a SQL operation that is so important that I took the time to talk about it. Even though we're not actually going to be using a join, I'm going to be giving you guys some examples of some joins. And it is a way to connect two tables horizontally. So whenever you write a join looks something along the lines of, I have my select query here. And it's selecting something from somewhere, right? This is our select query. I want to join something horizontally to it. I would write join. And then join almost works like another select query. When you write join, it says, what do I join? And you're writing another query. So you're writing like more columns. I want to join column 1 maybe I want to join column 2, and something, 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 from another table. So join this from, I am having a huge brain fart, from, I don't know, another table 2, on, and on is very important in a join. On tells you what you're joining with. So the idea of a join in SQL is for those two tables, your on condition is the relationship between your joins. So every time that on statement is true, that's when you join something onto it. And every time your on statement is false, that's when your SQL code knows not to join. And what you store in the join is just some kind of Boolean statement. For those of you who don't know what a Boolean is, it is just a true or false statement that for us is defined by equality. But it is all the joins look something like this. So there are, oh, yes? Oh, which code? The class average one, okay. Well, here, do you have a picture of this code? Mm-hmm. Yep. Yeah, you can take a picture of it so I can, yep. All right. All right, so within joins, there are 4 kinds of joins you will run into, and those are inner, left, right, and self-join. Inner joins are what you get if you just write the join keyword on its own. If you don't give it any other conditions to join on, you get an inner join. And inner join basically says that it will only give you records where I have exact matches. So maybe I'm trying to join 2 tables together. If something exists in both tables, then it will appear in your result. If it doesn't exist in one of the tables or it doesn't exist in either of the tables, you're not getting it. So this means when you perform an inner join, you might get incomplete data from both your tables. You're only going to get data that appears in both tables. So a great example of this might be, suppose you have some kind of website, right? And you're writing article. This website stores articles. But you have a chance for someone to publish anonymously. So maybe you have a site like this, or you have 2 tables. This one is publications, and this one is articles. And within the publications, you have your author. This is a key. And then you have your article key. All right, and you have some things in here. You have maybe article 1, 2, 3, and 4. Your article key appears here as well, and this is just some information about that article. Right? You might have author A who's published this, author B published this, author C published this, and maybe no one published article 4. Or yeah, it's an anonymous article. And then here you would know that, articles 1, 2, 3, and 4 show up. If I wanted to join these 2 tables with an inner join, only something that appears in both will appear. So let's say maybe because article 4 has no author, right? This is a null. Let's say that it's taking time to be reviewed. We don't know who the author is. Maybe we don't trust them. So it's not been published yet. So it hasn't appeared in our articles table. If we wanted to do an inner join on article key, right? I said article key, so that means that anytime the article key in one table matches the article key in the other table, that's when we join them. So a join would look something like this. We just go through both tables. This is the author. This is the article key, author key, article key, and then this is that whatever row about the article. We know that this first row here, this does appear in our table. It appears in both tables, so the inner join will accept it. B, 2 appears here, it will accept it. C appears here, it will accept it. D, this null value, article 4, does not appear in this join because it is not part of this article. On the contrary, if I were to say maybe, for whatever reason your website bugs, article 5 appears as a published, but article 3 is no longer published. Well, C appears here, no longer appears here. So C no longer shows up in our inner join. This is what an inner join is. It only has matches from both tables. Next up is the left join. Now, whenever we declare a join, we have a concept of a left and a right table. The left table is what you first select. So when I wrote out that select join earlier, I said select something from this table and then join on columns from this table. That first select is your left table, and what you're joining with that join keyword is your right table. So a left join states everything from our left table will 100% guaranteed appear in our result, but only matches from our right table will appear. So what does this look like? Well, let's say that rather than inner join, I have right join. Right? Now, what did I say? Everything in our left join. I have left join. Everything in our left table has to appear. So let's just write it out right now. C and null. Right? Maybe let's change this to something else. Maybe let's change this to like author K. There you go. Just because nulls are a bit finicky. We don't want to mess with null conditions. There you go. Now, author A published article 1. Article 1 appears here. Let's say this is maybe information X, Y, Z. So now, this column appears. Great. B appears here. 2 is in the articles table. So now, 2, we can join Y onto it. C appears here. Let's change this back to C. Let's change this back to 3. Well, C published 3. 3 is in our article table. There you go. Add that in. K is here. K published article 4. Uh-oh, 4 is not in our articles table. So what do? Well, we have to have everything in our publications table. On our right table, it's free-for-all. It's a free-for-all. You don't have to have anything. So because there's no match, we just say it's null. And in fact, if you put these two tables into SQL and you ran a left join and you tried to join on the article key, you would get a null. Because this appears in your left table, but there's no join, so it adds the column for you, but it just tells you, hey, I've got no information to join on. I don't know where it is. Now, right join is almost the same. Anything from the right-hand table will appear, and anything from the left-hand table will appear as long as there is a match. So this is the left join. Now let's change this to right join. Then I need an eraser. Then in our right table, we have 1, 2, 3, and X, Y, Z, right? So we know that 1, 2, 3, and X, Y, Z are guaranteed to appear in our resulting table. Now it says, all right, we're joining an article key. So 1's a key, an article key here. Hey, 1 appears here. All right, so it's in both. We will put it in. 2 is here, 2 is here. B goes in. 3's here, 3's here. C goes in. Nothing else. K doesn't even get considered because there is not even that extra column in the articles table. Only things from the article table will appear with 100%. So if there's 3 columns here, then you only actually get 3 columns in your resulting join. I really shouldn't have done that with my hand. Yeah, you would only get 3 articles or 3 columns in your resulting join because it's going to be the same as whatever your right table was. So that is the left and right table. They're actually just mirrors of each other. So a funny thing you might try later on at home if you go into DB browser and you try to do a right join, you get a very funny error that says right join is not supported by this build. And that is because they are so similar that SQL, DB browser for SQLite is just going to say, hey, rather than do a right join, just swap the left and the right tables, and everything will give you the same. But I thought that was funny because I tried to do a right join in a demonstration on Wednesday, and it just told me, nope, we don't like right joins. Now, self-join is an entire different beast because you don't see it very often, and it has a very niche use, but it is there. And it's what happens when you don't have the concept of a left or a right table, but instead you are joining the same table with itself. And you might think, well, if the table contains all of my information already, what's the point of copying that information over? And to that, I say, it depends on the context, but here's a great one. Suppose you are working in human resources and you want to track employees and their managers, right? So we have an employee table. And within this employee table, we have a bunch of columns. We have the employee number, and this number is our primary key. We have the employee name, and then we have, here's the kicker, their manager's employee number. Now, you can kind of see where I'm going with this. We have maybe employee 1, 2, 3, 4, 5, and they are Bob, Jane, A, B, and C. I am very, very creative. And then they have managers. Maybe Bob is the manager or maybe Bob's manager is Jane. Maybe Jane has no manager. Maybe A's manager is Bob, B is also managed by Bob, and C is managed by Jane. Now, suppose I wanted to make a new table and I wanted to see the manager information in the same table. This is where a self-join comes in. Remember, I have to join on some condition. What if I join on every time that the employee number is the same as the manager number? So what does a self-join? Sorry, I'm covering the board. What is the self-join from employee number to manager number look like? Well, a join is a horizontal, so now employee number 1, well, manager number 2 here, hey, manager number is in the employee number. So who is the manager for Bob? It's Jane. Maybe this is manager name. Who is the manager for Jane? You can't join on nulls, so Jane has no manager. Who is the manager for employee A? Well, manager is 1, their manager is Bob. Same here, Bob. And then here, Jane. And this is what a self-join will do. So this is when you have a table whose primary key also appears as a foreign key in that same table. And it sounds strange, it sounds niche as I say it, and it frankly is a little bit niche, but there are a few cases where this self-join comes up and it makes it very convenient. You don't have to make copies of tables anywhere. Now, aside from joins are horizontally combining tables. We also have the concept of a union. And a union is what we're going to use. And it is where we join tables vertically. So suppose I have 2 tables here. I have T1, and it's some table with, 3 columns, column 1, column 2, and column 3. And then I have table 2, Again, also 3 columns. Column 1, column 2, column 3. Well, a horizontal union or a vertical union using that keyword just takes both tables this is T1 union T2. Let's say union T2. And it's literally just putting the row, it's stacking them on top of each other. So maybe this one has A, B, C. This one has D, E, F. When you union them, you get A, B, C, D, E, F. All right, it's just running the rows. And when I do this, yes,
Does it keep or remove duplicate rows?
it will remove them. Actually, no, it will keep them.
So we can have like row 1, row 2 be exactly identical?
Yeah, so if you have, I don't know, if you have B appears here, right? It will show up twice.
Okay.
So when you do this table, you've brought it up a very good point. You have to be very careful. You might have ruined your primary key when you do this. And you'll notice later, when we do the union in DB, the table we end up with, it's a reporting table. We're not going to do any engineering with it. And so it doesn't actually have any primary key anymore. So yeah, you brought up a very good point. The primary key will no longer exist, especially if it appears in both tables. Another good thing to mention, table 1 and table 2, if you want to union them, they have to at least have the same number of columns. Now, I say at least because it differs from software to software. Some software will give you a warning that says, hey, we know that it's the same number of columns, but they all have different names, so we don't know what column goes where. We've given it our best guess. Some software will just stop you and say, hey, you can't do this union. The columns aren't the same name. So when you're doing a union, you should have both tables have the same columns with the same names. Now, aside from that, union doesn't have any conditions because you're literally stacking them on top of each other. There's no sort of indicator as to when it should appear or not. But we can use the union to create our final Acorn database. Because if you remember, in Acorn, it has all your classes sort of in a list. Here, all our classes are a table. But if we want them as a list, then we can union them. So if that's not what I meant to do. If I do that, if I go back into Python or into DB browser, and I make a new SQL query. Give me one moment. And I say select. And what do we want to select? Well, you don't actually get to see your assignment grades when you open up your Acorn academic history. You just get to see your grade. So I want the student number. I want the student average, and I want the class average. And we know, remember, these student and class averages, they only appear in our views. So we want to select this from maybe STAB52 view, right? We run this, yeah, that looks fine. Now, let's union. Union, select, well, because they're the same, I'm just going to copy and paste. The nice thing about union. And I'm going to do this from STAB57 view. I do this. Hey, we have like 100 rows here. That's way more than we had before. So we know the union's successful, but how do we tell the difference? This is the question you brought up. The student numbers here do repeat. They are designed here to repeat because of course prerequisites. If you want to take B57, you have to have taken B52. If you want to have taken C62, you have to have passed both 57 and 52. So there are clear repeats here, and we can't even tell the difference. Well, let's make a new column. Let's call this class. So if you want to make a new column, but you don't know what to engineer it as, you can give it a static value. So I'm going to say this is everything from STAB52, and that string is called the class. The same way, I can say this string, STAB57, is a column called the class. Oops. And now if I do this, now that class shows up. So class B52, and then if I scroll down, there's B57. If I do it one more time, and I put in the union, paste it in. I can now do the same thing, C62. Oh God, C62. And C62. Now if I run this, same thing, 57 and C62. So now all of them are here. If I were to select some random student, so let's pick this guy, 10028905529. Let's say I put this in a thing in parentheses, and I'm selecting from this table. Remember, I said select returns a table, right? So if we want to do from needs a table, we can just give it another select statement, actually. So let's say I'm going to select everything from this big engineered table that we have, and I'm going to do it where student number is equal to that person we just picked out, and that is 10028905529. If this is somehow your student number, I am sorry, I generated them randomly. These aren't your real grades. If I run this, hey, this is now that student's grades, and this is looking a lot like what you might see in Acorn. When you open up your Acorn academic history, you have the classes you took, maybe not your student number, but you would have your score. If you did credit, no credit, you would get no credit or credit, and then you would have the class average to compare it to. Now, there is one thing we are missing here compared to the regular Acorn kind of view, and you might have noticed that's the letter grade. Now, letter grade is something that is very finicky to do, and so I've actually done this ahead of time because, and I'm going to copy and paste it in, because as soon as I copy paste it in, you're going to see why I didn't write it in this workshop. Now, whoops, oh God. Let me drag this back over here, go over, give me my thing back. Where is my DB browser? There we go. All right. So if you will give me one moment. UTs, 5, DS3, setup. Hopefully this opens here. Yep. All right. So let's see what the student grade letter looks like. Right? Remember, if I want to add a new column, I add a comma, do that, and bam. That is not nice to look at. I literally I went online, I looked for our grading scheme, and I wrote this in. Please don't, you can take a picture of this. I wouldn't suggest trying to copy it in right now. Even looking at it, this looks pretty suffocating. It's a huge pain in the ass. There are many ways we can get around this. For example, I could, same way I did with class averages, I could have a table that has every number from 1 to 100, and then the corresponding letter grade. And then when I do this, rather than making, what is this, 13 case wins, I could just say, hey, round the student average to the nearest whole number, and then join that rounded value with whatever number appears in that mapping table I made earlier. And then I could do that same thing here with like 2 lines, and it's way easier. But for this, I want to give you an idea of the difference between what is SQL that works and SQL that works quickly. And you've probably seen this for like silly examples in Python where, check if is even, if number is 2, then yes, if number is 4, then yes, if number is 6, then yes, or you could just say divisible by 2. It's a very silly example, and I put it specifically like this. But there's our student grade. Now remember, student grade has to be consistent between all our unions, so I'm going to copy it into this select query as well, and also into this select query. This query is getting prettier and prettier with every paste. And now, if I were to run this, hopefully nothing breaks. Something did break. That's not good. Ah, yes, I have commas here. There you go. If I run this, now the student grade is shown. This guy willingly credit no credit C62 because he failed. Fair enough. Right? Student grade is here. We can do the same thing. That's right. I'm doing this a second time with the class average. The class average is literally the same code, except rather than student grade, I put in the class average. So I go all the way back up to the top. I add this comma back in, paste, bam, class average, and then, add the comma back in, paste, class average, add the comma back in, paste, class average, run this, bam, now the class average is here. And you can see I still have that original select thing. This is what you would see in Acorn, maybe in a different order, but you would get your score, you would get your grade, and then you compare that to your class average grade and your class average score. So we now have the perfect SQL query for this, well, somewhat perfect. Right, if I ran this without that original select, this is all their students, all their grades, all their class averages. I can save this as a view, create view, Acorn, as this select query. And if I run this and I go into my database structure, there's our Acorn view. If I browse that data, bam, this is our heavily, heavily engineered select query that we just made. So this is the extent of what we're going to do in the database. Now I want to get on to the actual pipeline itself, which is surprisingly way easier than this. So let me minimize this. So let's get to our pipeline. We're going to move into Python, so take some time to open up your Python development environment. And the pipeline we're going to make is, suppose we have your professor, you go to your professor and you say, hey, I want to retake this quiz or retake this test, and they say, okay, you'd retake it, you get a new grade. They have to update it on Acorn, right? This is a pipeline that might run manually every time someone does an update, or you might just have it run daily and check for updates. But the idea is that we're going to give it a new grade book in the form of a CSV file, and then it's going to take that and it's going to update the database we just made. So remember, all that stuff that we just did, it's in a database. It's in something called acorn.db, right? I'm going to write changes, so all of that change that we made, all those new tables, those new views, they are now saved in that one.db file. And if I close this database, they will still be there. So let me actually quit DB browser. Save. Sure, save. Oops. Acorn workshop. Save. Right? They now exist in that browser. So now let's move into Python and let's see how we can build this data pipeline. I'm choosing to do this in Python, and it's very commonly written in Python, but you might also see it within whatever cloud engineering tool you get. So I mentioned Microsoft Azure. There's options in there to build your own data pipeline called, I believe, Data Factory. Amazon Workspace lets you run scripts, and often it's just a pile of Python scripts and some orchestrator that says, hey, in the morning, run this script. Afternoon, run this script. Someone presses a button, run this script. So let us open up our Python editor. For me, I have it here. There we go. So I'm personally using Sublime Text. You don't have to. I wouldn't recommend using Sublime Text. I don't know why I choose to do it. But this is our Python thing. I'm going to change the syntax to Python so it's easier to look at. All right. Now then, the first thing we want to do in our Python sort of file, so actually I'm going to give you guys a chance to open up a blank Python file. If you're using VS Code, open up a blank project. Just get that ready for you. We're going to need two projects, or two packages. The first package is called, oh, I'm going to need to make this bigger. Can you guys see this in the back? No? OK. View, maybe in preferences, settings, set theme font, larger. Oh, perfect, I can just do. How's that? Good? Perfect. All right, import SQLite 3. SQLite 3 is great because I remembered earlier, you use it everywhere, and so Python actually comes with this pre-installed. You don't have to get a homebrew, look for packages or anything, it's just there. And then import CSV. CSV, comma separated value, it's a way of storing tables. And why are we using CSV? Well, if we look at that folder that we had downloaded, that folder is here, we notice we have these. new B52, new B57, new C62. If I were to open them, I've sampled 5 students from each of those tables, and I have changed their grade in some way, shape, or form. So maybe I made them declare credit, no credit, maybe they retook a test, maybe there was a policy to see that your highest midterm grade, or your highest of your final and midterm becomes your overall grade, things like that. I've done that with all of these. Now you might notice these aren't all the students. In fact, the way that SQL works and the way we're going to write this program, it's not going to matter. But it's worth noting that this here, I only have 5 students, so it's convenient for you guys to see. But this pipeline would work the same if you had your whole grade book and you were changing some things and leaving some things the same. So within here, firstly, let's read our CSV files. So let's read CSV files. And in order to do that, we would do with open, we want, let's say, do B52 first, new underscore stab52.csv. We want to open that in read mode as maybe, I don't know, B52 file. I'm going to make this a little bit smaller so my entire code fits in. Oh, actually, no, I can just make my window bigger. Can I please make my window bigger? There we go. And then within that, CSV reader is equal to csv.dict reader B52 file. Whoops, B52 file. Now, what is dict reader? You might have come up with other readers. Dictionary reader just takes every row in your CSV file and it returns it as a dictionary, where the keys of that dictionary are the names of your columns and the actual elements are, what's in the column themselves. And I'm going to save that as a list. So our B57 list is list is just each row in our CSV reader, row for row in CSV reader. Now let's take a look at what this looks like first things first. So print B57, this is supposed to be B52, excuse me. Now if I save this, and I save this in our sort of pipeline thing, where's I go to desktop, workshop student, I just save it in the same folder that you put your acorn.db in, so where you downloaded all those GitHub files, put it in that folder. I'm going to name this pipeline.py because it's a pipeline. Now I can go in here, I'm running this in terminal. This is iterm. I just opened up a new session, I changed the directory, and I'm going to do Python 3 pipeline.py. If I run that, it's a little bit hard to see, but this is a list. Can I make this bigger? Preferences, let's see if I can increase the font. Appearance, Windows tabs, panes, dimming. I don't think I can. Search, font. Nope, I can't change the font. Okay, so I will just explain this to you. For those of you who have seen what a dictionary is, this is just a dictionary. It is a list of dictionaries where every element in this list is a dictionary. So an individual element, if I can find my mouse, looks something like this. It has an element for student number, quiz 1, quiz 2, up to quiz 6, midterm, and final. So this is exactly what we saw in our SQL database, but now it's in a dictionary form. And we have a big old list of these, a list of 5 of these for each student that had their grade changed. We can do the same thing with the other two classes. So let's do the same thing with B57 and C62. So there's B57, and you just change everything to, 57, and then you change everything here to C62, no, C62, 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 C62. Let's check I didn't miss anything. Nope. Okay, so now we've got, yep. Oops, thank you. C62. I knew I missed something. All right, there we go. So now we've opened up all three files and we've saved them as convenient lists for us to use later. Now let's get on to the actual editing the database part. To connect to our SQL database, we want to first open it like any other database file. Rather than use open, SQLite has something called connect. So we have our database, which we'll save as DB. We can save it as Acorn. You can save it as anything you would want. Is called, or is equal to SQLite3 dot connect, and then you give them the file name of your database. Oops. This looks very similar to open. It's basically the same. You're opening this database, and with any reader, you get returned a cursor. Here, you need to get it yourself. So db.cursor is the cursor. I'm going to save this as cursor. And now we have a way to sort of edit and mess around with our SQL files. Now, I should notice, we can get to this point without having closed DB browser. But if you've ever tried to edit a text file or like a CSV file in Python, while you had that CSV file open, you get an error when you try to run your code, and it's like, oh, session is being used by someone else or something like that. It works the same as SQL. If you have your database open while you're running this Python script, unless you have space for more than one user, it's going to tell you that there's an error and you won't be able to run it. So at this point, it is helpful for you to like close down DB browser fully. Save all your changes, write them to the database, and then close it fully. But now that we have this, let's first update stab52. We are running a little low on time. And to update something, we're going to do for each student in B52, we're going to write a query for them. Oops. So this is the same as it would be as we did it in SQL, where it's literally just a string that we're going to pass through into SQLite3, and SQLite3 is going to say this is a SQL query, and we're going to run it. Now, if you don't know, in Python, you can do 3 single quotes, and that gives you a multi-line string. So now you don't have to worry about, doing new line characters or anything like that. You can just run it as is, and we're going to use a keyword called update. We're going to update stab52 raw, and why are we editing raw? Because our view is taking elements from our raw file. So we always want to edit from the raw file, and that will propagate through all of our tables. We're updating raw, and we're going to set quiz1. We want to change quiz1, quiz2, quiz3. We don't want to change the student number. By God, we don't ever want to change that student number. Quiz4, quiz5, quiz6, midterm, final, CR, and CR. And what do we want to change them as? Well, this is the reason I had it saved as a dictionary. Remember, all of the elements in our list, so every student in B52 is a dictionary. And in Python, you can use the format function on the dictionary. This is a thing called a kwarg, a keyword argument. And now we can just call the keywords in our dictionary, and they will appear in our string. So what do we want to set quiz1 as? Well, we want to set quiz1 as whatever quiz1 is in our dictionary. Quiz2 is whatever quiz2 is in our dictionary. Right? Oops. Oh, good. And we can do this. Oops. Yeah. Quiz 3, quiz 4, quiz 5, quiz 6 equals, this one is midterm. This one is final. And this one is CR and CR. Now, where are these coming from? Like, am I pulling, quiz 1, quiz 2 out of space? No. These are the keys in our dictionary. So if you ever go and print one of these dictionaries, you will see that their keys are exactly quiz 1, quiz 2, all of that. And the reason that that happens is because the original folder that we were looking at, that's what the names of the columns are. These say, this is B52, these say quiz 1, quiz 2, quiz 3. And so when your dictionary reader reads them, it's assigning them the same column values. And so for here, that works out perfectly. Now then, something of note, I have encased CR, NCR in quotes, which you wouldn't normally need to do in a string. But remember, this string, once we send it off to SQLite 3, it's being counted as a SQL query. And in SQL, if you don't cover something in quotes, it's going to think it is the name of a function or a table or something. It's the same as Python. And so when I pass this through, right now Python knows this is a string. But once you send it off to SQL, SQL will have no idea. You need to give it something that tells it it's text. So that's why I'm rewrapping it in double quotes. But now that I have my query, I can send this off to my cursor. I can say cursor.execute query, and it will send, the cursor will say, all right, I'm connected to this database, I got sent a query, I'm gonna try and run it. So there you go. I'm actually missing something here. Where do I wanna edit it? I wanna edit it where student number equals student number. There you go, that's very important. Where the student number matches, that's where you wanna edit your row. So now if I run this, I do this. This loop happens for every single student in B52. And at the end of that, kind of like how we had to commit and write our changes in our database, db.commit is the thing here. And once this function happens, once db.commit happens, those changes are written to the database. You can't change them again. You can't revert those changes, they've been written. So this is your kind of last chance option of, hey, make sure I didn't mess anything up. And normally you might have a bunch of if statements here to check hey, did my data write correctly? But for now, we're just gonna say it commits and it works. So now we've done this for B52. We can do the exact same thing for B57 and C62. So B57 has 3 assignments, excuse me. So update B57. And we can literally just copy paste this. Instead of B52, we want B57. And instead of quizzes 1 through 6, we want assignment 1 equals A1. Assignment 2 equals A2. Whoops. Assignment 3 equals A3. And midterm, final, these are all the same. So I believe that's everything we need to do. Yep. And then copy paste for update STAC62. C62, remember, rather than having assignments or quizzes, they have term test 1 equals term test 1. Term test 2 equals term test 2. I don't think I had term test 3. Nope, it's just 2 term tests. And then the midterm and the final. And we are changing everything from C62. I should change the updates as well. This needs to update B57 raw. This needs to update C62 raw. All right. And this is essentially the entire pipeline. So every time you think of Acorn, they say at the end of the day is when Acorn changes show up. At the end of the day, something like this in the background in the school systems is running, and it's taking all of your professors' grade books, and it's saying, hey, I'm gonna go through every record. I'm gonna get a full thing for you guys if you wanna take a picture. I'm gonna get every record, I'm gonna update it. And then this runs, and then that Python file runs, and then the next day it runs again, So let's take a look before I run this file, I'm going to save it. Right, before I run this file, let's open up DB browser again. I'm going to open up that database again, just so we have an idea of what has changed. Right? So if I click open, let's look for one of the students that we changed. Right, so if I were to, how can I do this? Right, if I move all of these down a little bit, click on this. Let's look at B52. So within B52, oh God, we have this student here that has changed, 100-291-5488. So let's just write it down, 100-291-5488. 291-5488, all right. So we'll keep track of what this student is doing. In our database, let's look at our acorn. So let's make okay, we have a new one. Let's do select everything from acorn where student number equals, what was it? It was 100-291-5488. If I run this, bam, these are that student's grades. They did, wow, they're not doing great. Okay, so these are that student's grades. And if I run this, so let's run this. It says, oh, I have a typo somewhere. Am I writing C62 twice? I am indeed. Yes, something I missed. C62 doesn't have midterms, they just have a final. This is a great way to check your code. Run this, midterm syntax error. What do you mean midterm syntax error? Final CR. Midterm is fine here. Right? Can you see anything wrong with this? Don't. Oh yeah, let's try and save. Nope, still says midterm syntax error on line 55. So it is up here. Okay, so it's this one that's failing to execute. Why midterm syntax error? Do I not have a midterm? Midterm. No, I have a midterm. Oh, comma. Gotta love Python and SQL. There we go, runs. Now, if I go into DB browser and I check this again, you will see their grades have changed. This used to be 42, something like that. Now it is 33. And if we look at C62, within their sort of thing, C62, we will see that student had their grade, in B52, not C62, had their grade changed to a 33 somewhere, apparently. Oh, the class average changed, sorry. They had their grade changed, I guess. Yeah. So, is there any questions before I stop and go for questions and answers? Immediate questions for this? I think I am going to, I'm going to make sure this code, there's no bugs, there's no real errors. I'm going to, comment the code so it looks nice. But I am going to send this out to people. I'll just put it into that same GitHub repo, so maybe a day or two from now, you'll see a completed version of this with all the SQL codes in there and this Python file so you can mess around with it yourself. But yeah, I'm going to leave the next, it says 10 minutes. I'll stay for full 30 minutes if you guys have questions or answers or questions you want to ask. Yeah. Sure. Okay. Do you have time right now, Aniki? Or? Yeah. So for now, would you mind waiting until I post the code in the GitHub repo, and then you might be able to compare them directly? Because is it the Python code that's not running for you? Or? Oh, okay. Have you saved that Python file in the same directory? So, DS3, yeah, that's fine. Save, okay. What is it saying? No such file in directory. Oh, interesting. Go back to that folder. It's right there, yeah. Go back, okay, go to Visual Studio or whatever code editing thing you were using. And do you have a way to show your directory? Oh, yeah. It says here, this is just in your users thing, so you save this somewhere else. Yeah, so maybe you can do File, and then Save As, and then now select the folder where you've placed it. Yeah, open, and then you can save it there, you can hit yes. Now try. There you go. Now it's printing. Okay.
For some reason, this view is empty.
This view is empty. Have you executed the SQL code?
No.
Create as select. Okay, we'll remove the create and as for now.
What?
I just delete these two lines, lines 1 and 2. And then run this query and see if it returns anything. Ah, that's why.
Okay.
Yeah, so if you can fix this, equals false, then else, and case 1. Then CR else. Are you missing a comma somewhere, probably? Not sure. Let me check your error code here. Over as class average, line 1 select comma, case 1 from STABC62 equals. Oh, you have 2 equal signs here.
Oh.
It's not like Python, you need 1. So if I run this, oh, there's still an error, but that's one thing fixed. CR else NCR end as student average, comma, class average over. Yeah, I don't actually know. Can you? All right, I'll help you after this. Is there anyone else that has questions aside from, code doesn't work or just generally? Yes. Sorry? So there are, as far as I know, in the university, not too many courses that will teach SQL. If there's a CS course, someone will have to correct me. I'm a math and stats major, but there is?
Yeah. So if you want to learn more about databases in general, this course called Introduction to Databases.
So
More comprehensive course for databases, but something more like even simpler would be CSE.
CSE 43? C4. There you go. And then, honestly, I'd say, well, the W3 schools is one thing. There are a few really good LinkedIn courses. If you have like LinkedIn Learning, there are a few really good LinkedIn courses that will go through each of them in detail. And they probably work through projects as well. So I would recommend doing those. And then if you have course credits, take that. So, yeah. Anything else? No? Great. We will end off this seminar here. If you still have questions, stay after and I will help. Yes. I'm going to try.